Welcome to this lecture on the log-normal distribution. Today, we are going to explore a fascinating mathematical concept that perfectly describes things that grow multiplicatively, like city populations, human wealth, and stock prices. By the end of this video, you will understand how to model and analyze data that compounds over time. Let us dive in. To understand the log-normal distribution, imagine you are rolling a snowball down a hill covered in fresh snow. As it rolls, it picks up snow, and the amount it picks up depends entirely on how big it already is. This is called multiplicative growth. In real life, human wealth and stock prices grow exactly like this snowball. If you measure the final sizes of many such snowballs, you will not get a symmetric bell curve. Instead, most are average sized, but a few become absolutely massive, creating a long tail stretching out to the right. This shape is the log normal distribution. Now that we understand the snowball effect, let us define this mathematically. A random variable x is said to follow a log-normal distribution if taking its natural logarithm gives you a perfectly symmetric normal distribution, which is the classic bell curve. The natural logarithm is simply a mathematical function that shrinks huge numbers down to manageable sizes. So if you have heavily right-skewed data and take the logarithm of every point, it forms a beautiful bell shape. Because you cannot take the logarithm of 0 or a negative number, a log-normal variable must always be strictly positive. This brings us to the probability density function, the mathematical formula that draws the exact shape of our skewed curve. Notice that the formula contains the symbols mu and sigma. It is absolutely crucial to understand that these are not the mean and standard deviation of the log-normal variable itself. Instead, they are the parameters of the hidden underlying normal distribution. The variable x represents our outcome and must always be strictly greater than 0. If you increase the value of sigma, the right-sided tail of the log-normal curve becomes much longer and thicker, meaning extreme values become much more likely to occur. Now that we have seen the formula, let us understand where it comes from conceptually. We start our derivation with what we already know, the standard bell curve. Let y be a normally distributed random variable with a mean of mu and a standard deviation of sigma. We write down the classic bell curve probability density function for y. Next, we define our log-normal variable x such that y equals the natural logarithm of x. To find the new probability density function for x, we must use a calculus technique called the transformation of variables. This chunk of the proof sets up the foundation for our final log-normal formula. Continuing our derivation, we substitute the natural logarithm of x into our normal probability density formula wherever we had y. But calculus requires us to also multiply by the absolute value of the derivative of y with respect to x. The derivative of the natural logarithm of x is simply 1 over x. We multiply our original bell curve formula by this 1 over x factor. This mathematical step adjusts the scale of our probabilities, stretching them back out to ensure the total probability still adds up to exactly 1. This scaling is exactly what creates the sharp peak and long tail of the log-normal curve. Let us visualize what this mathematical scaling creates. Here is the log-normal probability density curve. Notice how it starts at 0, rises sharply to a peak, and then stretches out into a long tail on the right. Because of this stretch, the center points do not line up in the middle like a bell curve. The mode is the highest peak, the most common value. The median sits further right, splitting the data in half. And the mean is pulled even further right by the massive values in that long tail. As we just saw in the diagram, the log-normal curve's stretched shape forces its central metrics apart. The mode represents the single most common value you would observe, sitting at the very peak. The median is the exact middle value, highly robust and not easily dragged around by extreme outliers. The mean, however, is the traditional average. The massive values in the long right tail pull the average up significantly. Because of this, for any right-skewed log-normal distribution, we always have a strict ordering, where the mean is greater than the median, which is greater than the mode. Here are the exact mathematical formulas to calculate these three central metrics. Notice how they all use the mathematical constant e raised to a specific power. For the mode, we subtract the variance from mu before raising e to that power, making it the smallest value. For the median, we simply use mu without adding or subtracting anything. And for the mean, also known as the expected value, we add half of the variance to mu. This mathematical structure perfectly guarantees our rule that the mean will always be the largest, followed by the median, and finally the mode. Let us put these formulas to work with an example. Suppose an electronic component's lifespan follows a log-normal distribution with an underlying mean of 5 and a standard deviation of 1.2. We want to find the mode, median, and mean. We start with the mode. We substitute 5 for mu and 1.2 for sigma. Squaring 1.2 gives 1.44. Subtracting this from 5 leaves 3.56. Raising e to this power gives approximately 35.16 hours as our most common failure time. Continuing our calculations, we next find the median. This is simpler. We just raise e to the power of mu, which is 5. This gives us approximately 148.41 hours, meaning half the components fail before this time. Finally, we calculate the mean. We take our squared standard deviation, which is 1.44, and divide it by 2 to get 0.72. Adding this to 5 gives an exponent of 5.72. Raising e to this power gives our mean. Evaluating that final exponent gives a mean lifespan of approximately 304.90 hours. Now we compare our three results. We clearly see that 304 is greater than 148, which is greater than 35. This perfectly confirms our theoretical rule that the mean is greater than the median, which is greater than the mode. The average is pulled extremely high by a small handful of components that happen to last a very long time. Now that we can find the center of our data, how do we find probabilities? To find the chance that our variable is less than or equal to a specific number, we use the cumulative distribution function, or CDF. Instead of doing complex calculus every single time, we can cleverly use the standard normal CDF. By translating our log normal problem into a standard normal z-score, we can simply look up the answer in a pre-calculated probability table. Let us look at the formula that makes this possible. This formula is a massive time saver. It says that to find the probability of x being less than a target value x, you first take the natural logarithm of x. Then you subtract the underlying mean mu and divide by the underlying standard deviation sigma. This fraction inside the parentheses converts your log normal problem into a standard normal z-score. The Greek letter phi represents the standard normal CDF. You just take your calculated z-score and look it up in a standard normal table to get your final probability. Let us see this formula in action. Suppose the income of a population follows a log normal distribution. The underlying normal distribution has a mean of 10 and a standard deviation of 0.5. What is the probability that a randomly selected person has an income less than or equal to 30,000? We need to find the cumulative probability. We substitute our target value of 30,000, our mean of 10, and our spread of 0.5 into the log normal CDF formula. Continuing our calculation, we first find the natural logarithm of 30,000 using a calculator, which is approximately 10.3089. Next, we subtract the underlying mean of 10 from this logarithmic value, leaving 0.3089 in the numerator. We then divide this result by the standard deviation of 0.5. This division scales our value correctly, giving us a final standard normal z-score of exactly 0.6178. Our calculated z-score tells us exactly how many standard deviations our target value is from the mean. We now look up the value of 0.6178 in a standard normal distribution table, or we can use a scientific calculator. The result is approximately 0.7317. In plain English, this final answer means there is a 73.17% chance that a randomly selected person from this population earns an income of 30,000 or less. This completes our probability calculation. Before we conclude, we must look at one of the most beautiful properties of the log normal distribution. You may know that if you add two normal distributions together, you get another normal distribution. But what happens if you multiply two log normal distributions? Because logarithms mathematically turn multiplication into addition, the product of independent log normal variables is perfectly log normal itself. This makes the distribution incredibly useful in finance, where multiple independent percentage returns are multiplied together over time to get a final stock price. Here is the mathematical rule for this multiplicative property. If x1 and x2 are independent log normal variables, their product is a brand new log normal variable. The new underlying mean is simply the sum of the individual underlying means. Similarly, the new underlying variance is the sum of the individual variances, which is exactly why we take the square root of that sum to find the new standard deviation. This elegant property allows us to easily model complex compounding processes over time, making the log normal distribution incredibly powerful for real-world applications. Let us summarize what we have learned. The log normal distribution is essential for modeling variables that are strictly positive and heavily skewed to the right due to multiplicative growth. By simply taking the natural logarithm, we transform this skewed shape back into a familiar, symmetric normal distribution. Remember the strict ordering where the mean is always the largest, and the elegant property that multiplying log normal variables creates another log normal variable. You now have a deep mastery of this topic and can confidently handle data that compounds over time.